different?
Keep going.
So the gravitational pull in space is obviously less than what's here on Earth, making you age more on Earth since it's more here and less out there.
I'm going to say no. You can make a general relativity argument for that. There is a general relativity argument for the gravitational pull or the gravitational field that they both experience and the difference in time there. That is a separate thing. You did touch on, I was hoping you were going to go in a slightly different direction. I think the direction you're going down now is not going to help us for this problem.
Is it like energy, the fact that one of them needed to get to that speed?
We have to assume that the rocket's already going that speed when the problem starts. However, you touched on potential issue there. Even if the rocket's, let's say the rocket's already going 0.99 times the speed of light, and it's zipping by the Earth, and there's some device which synchronizes their clocks at that moment that passes Earth. And then it comes back, the clocks are out of sync. What happens when the rocket and Planet X meet?
Different gravity.
Okay. Could be or not be. Not enough information.
The rocket has to stop and turn around, basically.
And how does the rocket stop and turn around?
Decelerates, gets to zero, and accelerates again.
Okay. What would cause that? This is a 251 question. What causes an object to change its velocity?
Acceleration and deceleration.
What causes acceleration and deceleration?
Force in the
Opposing
opposite
force.
I
direction.
think somebody just said it.
An opposing force.
Force. All right. That's the key difference between these two situations. The rocket is going to experience force acting on it. It has to turn around somehow. Even if it goes in a broad circle, there's still a force acting on it in order for it to go in a circle. The rocket has to have a force acting on it. The Earth does not. If I have the Earth not worrying about the orbit around the sun, the Earth is basically in the same position it was when the rocket went out, especially a year later. But there's no force acting on the Earth at this point causing the Earth to turn around. So there's physically something different acting on the Earth and the rocket here, and that eliminates that choice. So twin paradox resolved. There are other approaches to resolving the twin paradox. This is just one of them. And so there's a series of problems that I've done in the master set and all tasks where I have the twins, one goes out to a distant planet, comes back, and now their birthdays are no longer the same. They're off by, well, you calculate how far off their birthdays are now, and then how fast does the other one need to travel in order to get back for them to have the birthdays the same again. And then I throw in some restrictions so the answer is not however fast the first twin went. It's a fun little math problem. In theory, it's fun. No student has expressed that yet, but I'm just assuming. All right, some more bizarre stuff. I'm going to take like a 1 minute break. I'm going to let this continue to run. I need to grab something to drink, and then I'll be right back. And again, if anybody would like a hamburger, there are some right there. Feel free to take however many you want.
sure I can wrap my head around this.
Oh, my goodness.
All right. All right. So how fast does an 11-foot car need to travel to put into a 10-foot garage? Go. Or what do we know?
It's a 11-foot car.
Okay.
Can't put 5 pounds on a 4-pound bag.
Well,
Unless you hold
to its
it right.
own.
Yeah.
So,
Just because it's not tested for 5 pounds doesn't mean you can't handle it. However, I feel pretty sure that 11 feet is longer than 10 feet, and so when we want an 11-foot car so that it is completely inside our 10-foot garage.
That's enough to push the wall down.
Without pushing the wall down. Not till after it's already in. You can push the wall down afterwards.
Did you say something about the speed of light and perspective with it actually bending? Is this something-
Speed of light definitely pops into this. You say it's something actually bending?
You said something like, we think it's going straight, but in a perspective
Oh.
manner, it's bending, that's the only thing I
That's
can think of.
that's a general relativity thing, that's a,
You go back to
I can only go so
bending.
far down that path before I start running the screen.
do we use Lorentz factor at all?
Yes. We're talking about 2 different lengths here. It was up there. Yeah, Lorentz factor definitely is coming into play here. What would the Lorentz factor be?
I don't know what it is for length.
And the problems we've done so far, we started with the speed and we figured out what the Lorentz factor is. This time we're gonna figure out what the Lorentz factor is first and then figure out the speed to go with that. What does the Lorentz factor need to be to get 11 feet into 10?
Uh, 111?
Say it again?
111?
Not 111, but, all right, so first off, looking for the Lorentz factor here, how can I know that the Lorentz factor cannot be 1/11 at all?
Does it need to be greater than 1?
Or equal to? Yeah.
Okay.
Lorentz factor is greater than or equal to 1. So, I got my 2 numbers here. What do you think I'm gonna do in order to come up with a Lorentz factor bigger than 1?
11 divided by 10?
Yep. So my Lorentz factor is 1.1. We had a relationship that LP is equal to gamma L. And so one of these is 10, I guess that's 11 and that's 10. you can go through and try to figure out what's proper and what's not, and I'll make reference to the issue there when we're finished with this problem, because there's something else we need to do in order to fully analyze what's going on here. So gamma is 1.1, so 1 over the square root of 1 minus beta squared is equal to 1.1. Solve for beta.
0.416.
0.416. Units?
Velocity squared over speed of light squared.
Therefore, what are the units of beta?
Meter squared per second squared.
Oh, no. I thought you said something different. What is beta? The definition, the math.
V over C.
So the units of V divided by the units of C.
Cancel out.
Yeah, so it's just 0.416, which is, I think you said earlier.
Yeah, I said it first, I got myself confused.
Yeah, I wasn't trying to confuse you, but it happens in special relativity. All right, so if the car is going 0.416 times the speed of light, crudely a little over, I guess, little over 120 million meters per second, we get that 11-foot car into a 10-foot garage. That's from one perspective, but from another perspective, don't forget the car could be sitting there and the garage is coming towards it. And so we have to somehow resolve the idea that it works from one point of view, but not from another point of view. And to do that, we need to talk about simultaneity. So we set up a thought experiment. We've got a train car, doesn't have to be a train car, but train car, and I've got a device here in the middle that's going to detect light hitting it. I have light coming into it from the left and from the right, and I have someone else standing up here observing. So the car is moving to the right relative to the ground at some speed v. Now, when the train gets to this point, when the middle of the train gets to this point right here, that's supposed to be a person there. There's going to be two flashes of light coming from both sides of this. So when the train gets to there, this person's going to see these two flashes of light go off at the same time. And how does he know? It's because those light's going to get to him at the exact same time. Now, in here, he's going to say, well, the train is moving this way, and light that's flashing here is going to come at it from both sides. So I have light coming at it from the left and from the right, but the sensor itself is moving to the right, so this is going to hit it first. If the right side hits it first, the light will turn green. If the left or these hits it first, if left hits it first, or it's a tie, the light will be red. So right first, the light turns green. Right first, there we go. So if this light hits it first, this thing will turn green. If this hits it first or they hit it at the same time, it'll be red. So from his point of view, he says it's going to be green. Now, the person on top of the train is looking at this, and he says, wait a second, from my point of view, this thing is not moving at all, and so both bits of light should get to the middle at the same time. So therefore, it will be red.
Say that again?
All right. So, train car cruising along.
Gotcha.
When it gets to that point right where Joe is, right, so the shortest distance from Joe to the middle of the train, when that hits that minimum, there's gonna be two flashes of light that go off. So Joe sees them both go off at the same time. He's got his own detector. It hits his detector at the exact same time. Joe reasons that the train is moving this way, so when these two flashes of light go off, the light from here is going to be moving this way, in all directions, but this way, and the light from here is going to be moving that way. Because the train is moving off that direction, this light's going to hit it first. It's basically that the sensor is coming to meet it. So Joe says that the light will be green because this side hits it first. This side of light hits it first. Now, the person on the train right here is watching, and the person on the train says, these things are not moving relative to me. Therefore, when the two lights go off, they're still not moving relative to me. The light will, but the things that flash aren't. And so those two bits of light should get to the sensor at the exact same time. You follow at that time?
That last part's kind of long.
It would be like you're in a car. You're in a car in the back seat, and you take a pencil, pen, whatever. You take something and drop it. From your point of view, the thing falls straight down. From someone on the outside's point of view, that thing moves at an angle.
Oh, okay.
So similar here, from the person in the train's point of view, the light is basically, flash goes off, they're gonna hit the sensor at the middle at the same time. From his point of view, they're not hitting at the same time.
But it is hitting the green first.
All right, I will tell you this, it will be green.
Yeah.
What's wrong with that other point of view though? Why is it not red? Because none of this is moving relative to this person.
No force. There's no force of movement or gravity or anything in his point of view.
True, but
No
there's no change in the force acting on them, and the thing's cruising at it's
Right,
in
but the
dynamic equilibrium as it moves by.
But there's force on the light itself. Force that opposes the light itself.
Because you got one coming at you, you're coming at it. So I get why that's turning green first. And I get why that perspective, you might see red, you might say this might be red.
Because unaware of his surroundings, you would say that both lights meet at the same time, right? But the other person sees that there's another.
That's not the secret. I hadn't thought of it that way, so I was trying to see if I could make it work in my own head. I can't.
Because wouldn't you need, the photon doesn't have mass, and so you can't have a force on it.
So once the light has been released, I mean, there's something that creates the light, but the light basically starts out traveling at the speed of light.
Velocity is a force, correct?
No.
Or,
Change in velocity is related to force.
yes.
I will say that the light exerts a force. When the light hits the sensor, it will exert a force on the sensor.
Yes.
But
The speed that the light's going, the speed the light's going is then amplified by the velocity?
I'm still thinking of it from your headlight.
from the sensor's point of view, this light's approaching it at the speed of light, and this light's approaching it at the speed of light.
That's from the sensor's point of view.
Yeah, actually, from everybody's point of view, the light is traveling the exact same speed no matter what.
But it matters what direction you're going. Because you're going to the same direction as the green light.
You've got a force that's going towards it, but you have a counteracting force to the left.
Yeah, I don't think force is really gonna get
Not
there.
force, but a speed on the light. It's an addition.
All right, let's see if we change the question a little bit. If, from this person's point of view, if those two lights go off at the exact same time, they should hit the sensor at the exact same time. Is there anything wrong with that thinking?
No.
All right, from his point of view, if they go off at the exact same time, since the sensor is moving to the right, the light coming from the right will hit it before the one coming from the left. Is there anything wrong with that thinking?
No.
But both can't be true. There's gotta be something different between their situations here. It's not dealing with the forces involved.
This is distance,
So-
or like you said, the way you the position he's at.
Yeah, from where he is, if he sees those two lights go off at the exact same time, then that means these lights are birthed at the exact same time. And so this light will get there first because the light from the right-hand side is going this way, the sensor is coming that way.
So in his point of view, on top of the car,
Let's give them names.
okay.
Sue and Lou. All right, so from Lou's point of view.
So from Lou's point of view, would the ground be moving in the opposite direction of
Yes.
car? Would the light then also carry that same push that way from his point of view?
No, because the light's coming from, the thing that flashes is on the train. I mean, it's,
Okay. I didn't,
or even if it's on the ground. Let's just keep it on the train for right now,
okay,
simplify
yeah,
matters.
I didn't realize it was on the, okay.